First of all, thank you all for being here at the end of the conference and hearing me talk about things I don't know much about. This is a work that was, so first I want to acknowledge my students and postdocs and research faculty. Without them, they would, my group would not get anything done. And as many of you know, as faculty members, we don't get really to do research. We get to write lots of PowerPoints and proposals. So I'm thankful for having these fine folks do the important scientific work. This was a picture of my group taken, I guess, in 2024, and a few of them have since moved on to postdocs. One moved on to a faculty position, Lana Centra, Shelby Jenkins. But this work was done by a master's student and actually undergraduate student under my direction, Ashley Silverbow. This is her master's thesis work. And I also would like to acknowledge her sister who made the graphics that I'm using. I took Ashley's MS thesis and made it into this talk to present to you folks for work. I'd like to acknowledge the sponsor of this project, National Science Foundation in the US. My group's work is also sponsored by these other fine organizations. All right, let's talk about what we're doing here. Is this, can I use this, I guess? Yeah, there we go, perfect. So the goal of engineering is really to make programs work on a quantum computer. The goal of quantum engineering is to make quantum computers do something useful for us. Now, the quantum computers, even if they do get large, even if Ion Q's claims of 20,000 to 30,000 qubit volume prove to be true, will still need to be distributed among multiple machines. Now, the problem is that right now we don't have a quantum network to connect quantum computers. There are many people, including some in this room, who are very actively working on this, but we don't have repeaters yet. So what we have now are medium scale systems, hundreds of qubits maybe, that are linked by classical links. So my group's work on this project was basically trying to begin to answer a question of what happens when real world meets these high ideas of using quantum computing for actual quantum computation. So one solution to address the problem of modeling what happens is to use effectively virtual quantum states. This is known as the cut circuits or cut bell pairs or cut entanglement. And this was first proposed in this Journal of Mathematics, Journal of Physics A, Mathematics and Theory, and later also discussed in the circuit knitting paper and the transactions. The idea is to employ classical communication resources on the circuits which are separable, and then using them combine into something which statistically resembles what you're trying to do with a fully entangled input into a circuit. And obviously this has a cost, and this has all sorts of problems as far as overhead is concerned, but that's what we have now. So there is an experiment on this, very recent experiment by IBM people. Of course, it's published in Nature, as is all of these IBM papers seem to be. And what they did there was they used IBM's quantum resources to test this circuit cutting and show that it actually does in fact produce statistics of an entangled state, and we'll see it later, what they actually did, only when you cut it, right? Now, what they have thus simulated or emulated on their computers has implicitly perfect inputs, as well as no account for delays, which add to imperfections. So what Ashley's master thesis was about is incorporating some of these imperfections and seeing what happens and how these imperfections should be implemented. That's the question she was asking. How do we actually implement a simulation of classical effects on quantum systems using quantum computers? That was the underlying question. So this scratches the surface of this. We have done comparatively very little comparative to the digital twin work in classical systems. We have models of planes that are then put into air by the additive manufacturing processes. We're nowhere near that, but we're just trying. Okay, so what is a separable state? What is a cut state? Well, what you have is you have these two qubits, which are clearly separate systems, and there is a bunch of gates acting on them. What gates are acting on them is not really terribly important, except that they have to be carefully constructed. At the end of this, out comes what is a virtual bell pair. So if you apply a circuit that you desire to evaluate on a real bell pair to this, and then over multiple trials, sum up the outcomes of measurements, the measurement statistics will be exactly the same, mathematically the same, as if you have had an actual bell pair here, right? Now, the way you do it is by decomposing the density matrix into these two separable states, and then applying this quasi-probability distribution. When it's quasi, because the A's, the coefficient A's, even though they sum to unity, they can be negative. That's your output on this state, which is entangled, is exactly the same as if you had summed up these the output on these individual states, right? Now, all of this was described in these two articles. This is nothing all that new. And what is neat about this is that you can actually implement this on a quantum computer because, well, you don't need that many gates to do this. I mean, this is what you need to get this done. And in fact, the overhead here is this number of runs to reconstruct the original state, output corresponds to original state, and here it's 5. So you basically run it 5 times more than you would if you had access to an actual state, right? This is somewhat uncomfortable. Let's put on here. All right. So everybody clear so far? Good. Now, both the fact that you're using imperfect equipment to produce the bell pairs to begin with, as well as the fact that you have to hold these bell pairs in some kind of a memory, which is not necessarily coherent quantum memory, adds noise. Both of these sources of noise can be modeled via a depolarizing channel, which is the worst kind of channel that you can possibly imagine in quantum information theory. This depolarizing channel can in turn be described using the Stensper dilated unitary or the randomly applied polar operator. All of us who have taken information theory course should remember this. There is a third way. In this particular problem, we can also expand the quasi-probability distribution to make on the cut bell pair. So there are 3 ways to do this. Now, what Ashley was looking at is comparing these three ways and what happens when you actually try to implement this, all right? So just to briefly discuss what these three methods entail, for the time sprint dilated unitary representation, you have these boxes, which are the unitaries, and you have these input qubits, of which there's two, because that's how you represent a system. It turns out that if you transpile for arbitrary f within the granularity of the fidelity, fs fidelity that we're seeking, the Qiskit transpilation routine produces a circuit with 60 extra gates. Now, one could optimize this. One could potentially make it smaller. We did not want to spend the time to make it smaller. So we just wanted some results. It's not going to be that much smaller. It won't be an order of magnitude smaller. It's still going to be further large circuit that you have to deal with. As you know, from you can model any arbitrary unitary circuit using any number of these gates available in Qiskit. So 60 sounds about reasonable, right? For randomly applied Pauli operator, well, you just add 10 extra gates and 6 extra qubits. Extra qubits basically serve as the random input when you measure them, and it works fairly well in that way. Now, what it depends on is availability of each particular Pauli gate. Here we show it with the Y gate, but in reality, you could just have X, Y, and Z. And it turns out that actually this does matter. How you implement this does matter. And finally, to extend the quasi-probability distribution of decomposition, we add these two identity rows and add the two remaining missing basis states that are not in the original quasi-probability composition, all right? Now, how do we measure whether there was entanglement? We employ two methods. We look at stabilizers, and basically what we're interested in is making sure that this graph state, which I'll have a picture of in a more tenable way, is in fact entangled, effectively entangled. Effectively meaning that the virtual entanglement bell pair produces the result that we expect it to produce corresponding to an actual bell pair. And we can take these stabilizers, compute these, and if the witnesses are less than 0, then we have entanglement. Also, we can lower bound the graph state fidelity using this expression, and anything above 1/2 indicate entanglement, right? So those are the two measures we picked. And here is the actual picture of the graph state. And what we are modeling is, suppose that 0 and 5 qubits are not entangled. We have 6 and 7, which are. We have, then we perform the bell swap on 6 and 5 and 0 and 7, and we entangle 0 and 5. But before we get to do that, there is fidelity degradation on 6 and 5. So that's what we're effectively modeling here. And the full circuit looks like this. This includes the measurement of the stabilizers. So the total number of runs depends on the number of separable states that we employ. For the quasi-probability distribution, there are 7 of them. For all others, there's 5. And there's also the same number of stabilizers for everything. We use 10,024 shots per run and when we calculate these results that we get. So the setup is we use an IBM Torino simulation. When Ashley did this work, we have not yet had access to the real IBM quantum computers, which the simulation has gate noise. It models that really well. it has the T1, T2 times, and we can also add a delay. We can control a delay between any gates. There's like a gate you can insert, just delay things, and it's gonna idle a circuit, and if it exceeds the decoherence time, your qubits are gonna die. But we're gonna assume initially 10 nanosecond classical delay. We also had access to IQM's Emerald machine, which only implements X and CZ gates, which is going to be important later on. To go around this limitation for the non-native gates, Y and Z, we had to implement them using Hadamard transformations and such. So IQM does not have, we didn't have enough qubits or connectivity on the qubits to actually implement the unitaries. We need 60 gates for that, if you recall. The noise is variable. We don't know where it is. We never know where it is. Sometimes the machine is off. There is an unknown hardware-determined delay in everything that IQM does, including response to the customer service queries. And we're gonna assume a 99.6 initial fidelity for both. So we basically degraded our bell pairs, virtual bell pairs, to 99.6, right? So let's look at the simulation results first. These show the stabilizer values and the graph state fidelity lower bound. And what one sees is what to expect to see. The stabilizer values are lower for the virtual qubits, the 0 and 5. For the rest of them, they're good. There is, right now, we have degraded qubits to 99.6, so there is that, but you can see that these are not really affected by degradation because we were not trying to degrade them. And for the graph state fidelity, the picture is the same. Now, what's interesting here is that the unitary seems to not behave as well, and that is because of all the gate noise that is modeled in the IBM casket model of the Torino machine, right? So there's no variability whatsoever in noise. There is no delay here, though we do add delay later. It's basically a simulation, right? Now, what's there's delay for 10 nanoseconds, we didn't vary it yet. Now, what's interesting is if we add the results from the hardware measured on top of the simulation results. So these faint lines, these are simulation results. And notice we do not have the line corresponding to the unitary because we could not implement the unitary on a IKEA machine. Well, if you look at this closely, you'll see immediately that the polygate approach is really terrible. In fact, it actually affects badly the neighboring qubits as well. And the reason for that is because IQM doesn't have native X. No, it doesn't have native Y and Z gates. So to implement Y and Z, we had to use multiple gates. To implement X, there's just one gate. What happens when your signal goes through more than one gate? It requires more noise proportionally. This is a reflection of that. So if you can avoid using more gates to do noise on your machine, on your quantum machine, you should endeavor to do that. If you're not, then you have to account fully, you have to build a model of what your actual channel should look like and not blindly apply the one-third probability of using each of the X, Y, and Z gates, right? So it's not 1/3. think it's 1/4, but no, it's 1/3. Never mind, it's 1/3. So in any case, the hardware noise also varied a lot per run as well. And what's interesting is that the QPD QPD implemented the quantum. Thank you. The quantum quasi-probability distribution was did pretty well. I mean, it's close to the ideal. So that's so if you can simulate a circuit, you're good. But if you have to actually use quantum hardware to simulate noise, you have to be very careful, right? So that's the lesson for this. Now, what we also did is we swept the initial fidelity. So it will be the fidelity of the state that we're inputting at 0, 1 qubit, 0, 5 qubit. And we can see that the stabilizer values linearly depend on it, as we expect, as does the graph state fidelity. So this is good news. That the system behaves just as we expect it to behave. We have what we were looking for here. And what this also says is that the computer noise clearly dominates, because you can see that the rest of these are fairly low fidelity after all that. We also did a delay sweep on simulation, because a QM computer doesn't allow us to actually do that. And here, the takeaway is that what we needed to claim to have entanglement is about 90% fidelity. And you can see that it dropped below 90, somewhere between 10,000 nanoseconds and 100,000 nanoseconds right here. And that corresponds to a distance for a photon flight, time of flight of a photon, ideal, no kind of diffraction or slowdown silicon included. We did use the speed of light in silicon, but we didn't include any transitions. And this, it's about between 2 kilometers and 20 kilometers. So it corresponds to a quantum data center network, if one can build such a thing. I would also like to note that we have done a study where we used a model for placement of quantum compute nodes at the local exchange locations in Manhattan. This is ILEC network. So we kind of said, okay, what if phone companies put their quantum computers where they have their presence in Manhattan? We had a map of those somehow. And those are about 5 to 10 kilometers apart. So we're good if we're going to build a quantum network in Manhattan. In conclusion, this was a kind of very first step towards evaluating distributed quantum computing, distributed part of quantum computing, distributed part of distributed quantum computing, that's what I want to say, on an actual quantum computer. We did show that the initial fidelity needs to be at least 90% to get to what we need. And we showed that the decoherence due to the communication delay does limit the network size that we can possibly get out here, which as we would expect. What was unexpected is the fact, and we should have expected this, but you actually don't really expect until you see it reflected in data, is that not having native gates for the full poly set does hurt in this model. And I bet it also hurts on actual implementations of quantum programs when you run them as well. Now, future work. We want to try actual bell pairs, not virtual ones, because all of this can be applied to actual bell pairs very simply. And that would be the first question you should be asking. Why the hell did we not try it on actual bell pairs? We just wanted to make Ashley's life a bit harder. I think that's what the reason was. But really, we thought it was just interesting to try this. And we're curious folk, and we decided that's what we're going to do. But we will do this on actual bell pairs. Ashley, even though she's not NVIDIA, is keenly interested in finishing up this paper and submitting it. We also got access, thanks to Jake and Beta, whom I met at the Quantum World Congress, and who mentioned that there is a program at IBM that they can just give you minutes or hours on their machines to use if you have a real bona fide useful quantum computing project, which this was deemed to be. We have the time on IBM machines. We're gonna run this on actual IBM hardware. Their hardware is arguably more advanced than IQM, so hopefully it's gonna work better. And the more future kind of for a different student like work, would like to actually look at the rates of entanglement generation and see how that impacts the picture. And finally, it would be really nice to find an actual bona fide quantum algorithm that would use these graph states as input. And someone mentioned Steam codes, and I am maybe, I mean, that'll be really, really small Steam code, but we can try it, I guess. So if anybody has any ideas, let me know. And that concludes my talk. Thank you very much for attentively listening. And I'll take any questions that you have and might not answer them because unfortunately the person who did all this work isn't here, and she is the mistress of the quantum computing simulation. So I'm quite incompetent in this stuff. All right, any questions, please?
Thanks a lot. Very nice talk. I'm no expert, but in the graph where you showed simulations and you superposed the real implementation, yeah, here. So there's one bar that goes negative on the left.
The stabilizers can be negative. Stabilizer values can be negative. These are just measurement values. That indicates that things are really bad. Really, really bad.
Thanks.
Any other questions? Can you also comment on something on the negative probabilities that is there?
Oh yeah, so this is a so quasi probability distributions are actually fairly common in quantum information. If you have where is this thing? Yeah, there we go. If you have seen the kind of Gaussian quantum information theory stuff, you'd remember that some of the functions in the continuous variable domain are quasi probabilities in that they integrate to unity like probability does, but can take negative values. And here by necessity this has to be true. So that's basically what they are. Now I don't have the coefficients here. I think they're found in these papers that I've quoted, but it's fairly easy to construct these for small states, but for large states it takes, I think, a bit of work. So
thank you. Do we have more questions?
We could just there we go.
Hi, thank you for that nice talk. You mentioned in the end that you would like to use actual bell pairs instead of virtual ones. So as far as I understood, the virtual bell pairs come basically from this LOCC simulation of things. And I thought this is exactly what you wanted to model. That because basically actual bell pairs according to current network technology are still too expensive or not really realizable for the lack of quantum repeaters. So I thought this is kind of the point of the experiment, to see how well you can be with
Right.
with this technology. How is it?
I mean, it's they work pretty well. I mean, if you look at these graphs, in the ideal case, they work fine. This is the quantum quasi-probability distribution approach. The problem is the overhead. I mean, you can do anything. You can do quantumly classically as long as you're willing to pay the price for it, and this is the price. Now, doing this with the bell pairs, the reason for this is to assess what would happen if one generates actual bell pairs, tries to transmit them over network, and have them subject to this noise. I mean, we basically replacing this mechanism right here with a bell pair. So there'll be a bell pair generated here, the H and the Hadamard and then the CZ. And we would then apply the fidelity gradation, same as we have done, and push it through. Now, why we did not do this for master's thesis, I actually just ran out of time, and she was really wanted to she read this Nature paper and wanted to redo it. And I said, yes, it's a good endeavor for a master's thesis. I like them to do what they feel is right. And it was more complicated than actually just using bell pairs. So, yeah.
So the goal with the actual bell pairs would be to see what the effect of this fidelity degradation is, or what you can still do.
Yes. So basically,
Okay.
So the question that one might ask is, we have a bunch of gates here to generate these virtual bell pairs, right? So these are different gates than the ones you'd use for actual bell pair generation. What's the impact of that? Is there noise that propagates somehow downstream into the other qubits, or down to the network itself? So that would be a valid question to ask. Perhaps what we'd find is virtual bell pairs might actually be better than real bell pairs. We don't know. But
when do you expect to run this on original, like real bell pairs?
Well, so our grant of free time from IBM expires, I think, in about 3 months. So my hope is that we'll get this done before then, obviously. Now, Ashley just started her work at NVIDIA, and I think that she got immediately promoted due to her excellent performance during her internships there. So she is a bit busy, and she's moving to a new place. I don't want to push her too much, because first of all, I no longer employ her, NVIDIA does. She's doing this voluntarily. Really, I'm just advising her on how to write this into a journal paper. She might want to come back to do the PhD at some point in time when she gets tired of making money at NVIDIA, making things which actually benefit people directly, as well as being an outstanding manager to her team. I think she now has immediately got like 2 reports. So she's great. I'm very happy for her, and I think that she'll do great whatever she does. But I think she wants to get this paper done too. So hopefully within 3 months we'll see results. Yeah.
We would also love to see the results. So let's thank the speaker again.